This is SpaceTime Series 20, Episode 65, coming up on SpaceTime. Counting down to the Great American Solar Eclipse, Precursors of life discovered on Titan, and Dragon flies a cosmic ray mission to the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The United States is now in final countdown mode for the August 21st total eclipse of the Sun, which will see the Moon block out the solar disk along a 113 kilometre wide path of totality, stretching from the northwest Pacific coast of Oregon to the Atlantic coast of South Carolina. The spectacle actually begins in the North Pacific Ocean south of the Aleutian Islands, before reaching the continental United States at Lincoln Beach, Oregon at 9:06 in the morning Pacific Daylight Time, with totality occurring at 10:19. The path of totality then passes through Idaho, Wyoming, Nebraska, Kansas, Missouri, Illinois, Kentucky, Tennessee, Georgia, and North Carolina, before finally reaching Charleston, South Carolina, where totality will begin at 2:41 in the afternoon Eastern Daylight Time, with the eclipse ending at 4:06. The eclipse finally draws to a close over the mid-North Atlantic Ocean, west of the northern African coast. The good news for people in the continental United States is that if you're outside the line of totality, north or south of it, you'll still see a partial eclipse, in which only part of the Sun's disk will be covered by the Moon. Mind you, the further away you are from the centre line of totality, the shorter the eclipse duration will be. Eclipses occur because although the Moon's 400 times smaller than the Sun, it's also 400 times closer, and so the two appear to be about the same size in the sky as seen from Earth. Normally, the Moon's orbit appears to cross the sky slightly above or below the path of the Sun. But every 18 months or so, the lunar orbit places the Moon directly between the Sun and the Earth, resulting in a solar eclipse. Solar eclipses occur on new moons. Usually 2 weeks before or after a solar eclipse, there'll be a lunar eclipse because the Earth will pass directly between the Sun and the Moon. Consequently, the Earth's shadow will cross the face of the Moon, often turning the Moon blood red. In fact, we had one of those in the skies above Australia 2 weeks ago. As a solar eclipse occurs, the Moon begins to slowly pass in front of the Sun, and a partial lunar shadow, or penumbra, crosses the surface of the Earth. Now, this can last for over an hour, as more and more of the Sun is hidden by the Moon. Then, just before totality occurs, the crest of the Sun converges to a single bright, brilliant white diamond of sunlight, as the last bit of the Sun's bright disk shines along the edge of the Moon, and the first glimpses of the Sun's atmosphere or corona create a ring around the Moon, a stunning effect known as the diamond ring. In the last fleeting moments before totality, the diamond ring breaks up into a string of beads, created as the Sun's rays shine through low-lying valleys between the mountains along the limb or edge of the Moon. Once this effect, known as Bailey's beads, ends, the Moon has completely covered the entire disk of the Sun, and you're in totality. During totality, the darkest part of the Moon's shadow, the umbra, crosses the surface of the Earth. People along the path of totality will view a total eclipse, which on the 21st of August will last for up to 2 minutes and 40 seconds. During this time, the skies will go dark and stars will begin to appear. It'll also suddenly get noticeably cooler. Birds will start roosting, and you'll be able to see the Sun's tenuous outer atmosphere, the corona, glowing milky white. Often, explosions on the Sun's surface, called prominences, will appear as spectacular bright pink or red clouds stretching above the lunar limb. Now, during all this, if you get a chance, check out any shadows or speckles of sunlight which you may see on walls or the ground. They'll take on an unusual crescent shape, something that only happens during eclipse. And one thing you must remember above all else, never look directly at the Sun, unless of course you're wearing special eclipse glasses or number 14 welder's goggles. You're listening to SpaceTime. I'm Stuart Gary. NASA's taking advantage of the August 21st eclipse by either carrying out or funding some 11 ground-based science investigations across the United States. 6 of these will focus on the Sun's corona. Though scientists commonly study the corona from space with instruments called coronagraphs, which create artificial eclipses by using a metal disk to block out the sun's face, there are still some lower regions of the sun's atmosphere that really only become visible during a total solar eclipse. Because of a property of light known as diffraction, the disk of a coronagraph must block out not just the sun's surface, but also a large part of the corona in order to get crisp images. But because the moon's so far away from Earth, some 400,000 kilometres during the eclipse, diffraction isn't an issue, and so scientists are able to measure the lower corona in fine detail. The sun constantly releases a flow of charged particles and magnetic fields known as the solar wind. This solar wind, along with more violent eruptions of solar material, known as solar flares and coronal mass ejections, can influence Earth's magnetic field, sending particles raining down into our atmosphere. And when intense enough, these geomagnetic storms or space weather events can damage satellites, cause power grid blackouts on the ground, disrupt communication systems, and affect GPS navigation signals. Scientists are able to track these solar eruptions as soon as they leave the sun. But the key to predicting exactly when they'll happen in the first place could lie in studying their origins in the magnetic energy stored in the lower corona. Scientists at the High Altitude Observatory in Boulder, Colorado, will use new instruments to study the magnetic field structure of the corona by imaging this atmospheric layer during the eclipse. The instruments will image the corona to see fingerprints left by the magnetic field's invisible and near-infrared wavelengths from a mountaintop viewing point near Casper, Wyoming. One instrument, PolarCam, will use new technology to obtain novel polarization measurements and will serve as a proof of concept for use in future space missions. Scientists want to compare the infrared data being captured here with ultraviolet data recorded both by NASA's Solar Dynamics Observatory and by the joint NASA-Japan Hinode satellite. The study will help researchers understand how light across the entire spectrum forms in the corona. The results will complement data from an airborne study imaging the corona in infrared, as well as another ground-based infrared study on Casper Mountain using a spectrometer to collect light from the sun as part of the most complete infrared survey of light emitted by the corona ever undertaken. The data will help scientists characterize the corona's complex magnetic field, crucial information for understanding and eventually helping to forecast space weather events. Meanwhile, over in Oregon, scientists from NASA's Goddard Space Flight Center in Greenbelt, Maryland, will point a new specialized polarization camera at the corona, taking a series of long-duration exposures at 4 specific wavelengths in just over 2 minutes. These images will capture data on the temperature and speed of solar material in the corona, measurements which can only be obtained by Earth-based observations during a solar eclipse. Typical coronagraphs use a polarizer filter in a mechanism that turns through 3 angles, one after another, for each wavelength filter. This new camera is designed to eliminate this chunky time-consuming process by incorporating thousands of tiny polarization filters to read light polarized in different directions simultaneously. The answer to another scientific mystery also lies in the lower corona. It's thought this region may hold the secret to the long-standing question of why the sun's solar atmosphere reaches such unexpectedly high temperatures. See, the corona reaches temperatures of well over 1 million degrees. That's far hotter than the 6,000 degree surface temperature of the sun. And of course, that's really counterintuitive because the sun's energy is generated by nuclear fusion in its core, where temperatures reach 23 million degrees. Now, usually, temperatures go down consistently as you move away from the heat source, in this case the sun's core, through the sun's surface, and then out into the atmosphere. It should be the same physics which explains why it gets cooler the further away you move from a fire. But for some strange reason, that's not happening with the sun's atmosphere. Instead of getting cooler, it gets hotter again. Scientists suspect that detailed measurements of the way particles move in the lower corona could help them uncover the mechanism that produces this enormous heating. So scientists will take images of the lower corona in polarized light. Now, we've been talking about polarized light a fair bit so far, so we better give you a bit of background. Polarized light occurs when all the light waves are oriented in exactly the same way. It's produced when ordinary unpolarized light passes through a medium. In this case, it's the electrons of the inner solar corona. By measuring the polarized brightness of the inner solar corona and then using numerical modeling, scientists can work out the number of electrons along the line of sight, essentially mapping the distribution of free electrons within the inner solar corona. Mapping the inner corona in polarized light to reveal the density of electrons is a crucial factor in modeling coronal waves, one possible source for coronal heating. A NASA citizen science project called Citizen Kate will gather unpolarized eclipse imagery from across the United States. Combined, these polarized and unpolarized light measurements could help scientists address the question of the solar corona's unusually high temperatures. Meanwhile, researchers from the University of Hawaii will be imaging the sun during the eclipse from 5 sites across 4 different states located about 1,000 kilometres apart each. This will allow them to track short-term changes in the corona. They'll use spectrographs to analyse the light being emitted from different ionised elements in the corona. The research team will also use unique filters to selectively image the corona at certain wavelengths, allowing them to directly probe the physics of the sun's outer atmosphere. Now, with this data, they'll be able to explore the composition and temperature of the corona, and because spectroscopy can also give you a Doppler shift, they'll also be able to measure the speed of the particles flowing out from the sun. Different wavelengths, or colours, correspond to different elements, nickel, iron and argon, which have lost electrons, that is, they've been ionised in the corona's extreme heat, and each element ionises at a specific temperature. By analysing all this multitude of data together, scientists hope to better understand the processes that are heating the corona. Another experiment, this one by scientists with the National Centre for Atmospheric Research, will use a Gulfstream 5 research aircraft to take infrared measurements for about 4 minutes to help scientists better understand the solar corona's magnetism and thermal structure. Meanwhile, teams from the Southwest Research Institute in Boulder, Colorado, will use 2 of NASA's high-flying WB-57F research jets to take observations from twin telescopes mounted in the nose of the aircraft. From their high-altitude perches, they'll be able to capture some of the clearest images of the corona to date, and some of the first ever thermal images of Mercury, revealing how temperatures vary across the planet's surface. Mercury is difficult to observe because it's usually washed out by the bright daytime sky or distorted by the atmosphere near the horizon at twilight. Scientists plan to measure Mercury in near-infrared in near darkness and through very little atmosphere. They hope to use infrared measurements to calculate surface temperatures over Mercury's entire night side. How temperatures change across the surface of Mercury will give scientists information about the thermophysical properties of Mercury's soil down to depths of a few centimetres, something that's never been measured before. You're listening to SpaceTime. I'm Stuart Gary. A total solar eclipse provides scientists with a great opportunity to study the Earth under uncommon conditions. In contrast to the global change in light that occurs every day at dusk and dawn, a solar eclipse changes illumination of Earth and its atmosphere only under the comparatively small region of the Moon's shadow. This localized blocking of solar energy is useful in evaluating science's understanding of the Sun's effects such as temperature on our atmosphere. Of special interest is the impact on Earth's upper atmosphere, where solar illumination is primarily responsible for the generation of a layer of charged particles called the ionosphere. A total solar eclipse will cause a sudden loss of the extreme ultraviolet radiation which actually generates this ionized layer of atmosphere. This ever-changing region expands and shrinks based on solar conditions, and so scientists will be able to study this region to improve their understanding of the Sun's relationship with the ionosphere. Stretching from about 90 kilometres to 800 kilometres above the Earth, this is the near-Earth region of space where most satellites orbit. It's also where radio signals are reflected back towards the ground. The eclipse will effectively turn off the ionosphere's source of high-energy radiation. Without this ionizing radiation, the ionosphere will relax, suddenly going from daytime conditions to nighttime conditions, and then back again immediately after the eclipse. The tenuous ionosphere is an electrified layer of the atmosphere that reacts to changes from both the Earth below and from space above. Now, such changes from both the lower atmosphere and also from space weather can manifest as disruptions in the ionosphere that can interfere with communication and navigation signals. Engineers from Virginia Tech will use the eclipse to pin down ionospheric dynamics, while scientists from the Massachusetts Institute of Technology's Haystack Observatory will look at how much solar radiation is blocked, the area of land it's blocked over, and for how long. Combined with measurements of the ionosphere during the eclipse, they'll have information on both the solar input and the corresponding ionospheric response, enabling them to study the mechanisms underlying ionospheric changes better than ever before. Tying these studies together will be the use of automated communication and navigation signals to probe the ionosphere's behaviour during the eclipse. During typical day-night cycles, the concentration of charged atmospheric particles or plasma waxes and wanes with the sun. During daytime, ionospheric plasma is dense, however the production disappears as the sun sets. Charged particles then begin to recombine gradually during the night and the density drops. So during the eclipse, scientists should see this process occurring over a much shorter time interval. The denser the plasma, the more likely these navigation and communication signals are to bump into charged particles along their way from transmitter to receiver. These interactions should refract or bend the path taken by the signals. During the eclipse-induced artificial night, scientists expect stronger signals because the atmosphere and consequently ionosphere will absorb less of the transmitted energy. The receivers will monitor the phase and amplitude of the transmitter signals. When the signal wiggles up and down, that's entirely produced by changes in the ionosphere. Using a range of different electromagnetic signals, scientists will send signals back and forth across the path of totality. By monitoring how their signals propagate from transmitter to receiver, the researchers should be able to map out changes in the ionospheric density before, during and after the eclipse. This will allow them to compare the well-defined eclipse response to the region's baseline behaviour, allowing them to discern the eclipse-related effects. The ionosphere is roughly divided into 3 regions in altitude based on which wavelengths of solar radiation are absorbed. These regions are referred to as D, E and F, with D being the lowest region, E in the middle and F the uppermost. A team of researchers from the University of Colorado in Boulder will probe the D region's response to the eclipse at very low frequency or VLF radio signals. This is the lowest and least dense part of the ionosphere and because of that, the least understood. The D region has implications for communication systems actively used by the military. VLF transmitters are vital to navies to communicate with submarines underwater. They're also used in some engineering operations. As part of this research project, the scientists will use the US Navy's existing network of powerful VLF transmitters to examine the D region's response to changes in solar output. Radio wave transmissions sent from North Dakota will be monitored at receiving stations across the eclipse path in Boulder, Colorado and Bear Lake, Utah. This D region data will then be combined with observations from several space-based missions, including NOAA's Geostationary Operational Environmental Satellite, NASA's Solar Dynamics Observatory, and NASA's Ramity High-Energy Solar Spectroscopic Imager. Combined, they should be able to help categorize the effect of the sun's radiation on the ionosphere's D region. Meanwhile, other teams will be looking further up at the E and F regions of the ionosphere. Using more than 6,000 ground-based GPS sensors alongside powerful radio systems at MIT's Haystack Observatory and the Arecibo Observatory in Puerto Rico, together with data from several NASA space-based missions, the MIT-based team will also work with citizen scientists who will be sending radio signals back and forth over long distances across the path. The team will use the data to track travelling ionospheric disturbances, which are sometimes responsible for space weather patterns in the upper atmosphere and their large-scale effects. These disturbances in the ionosphere are often linked to a phenomenon known as atmospheric gravity waves, which can also be triggered by eclipses. The Virginia Tech-based team will station themselves across the country in Oregon, Kansas, and at Shore Air Force Base in Sumter, South Carolina. Using state-of-the-art transceivers known as ionosodes, they'll measure the ionosphere's height and density and combine their measurements with data from a nationwide GPS network and signals from the Ham Radio Reserve Beacon Network. The team will also utilise data from high-frequency radars along the eclipse path in Oregon and Kansas. They'll look at the bottom side of the F region and how it changes during the eclipse, as this is the part of the ionosphere where changes in signal propagation are strong. The work could one day help mitigate disturbances in radio signal propagation, which can affect AM broadcasts, ham radio operations, and GPS signals. Another experiment, this one by a research team from Boston University, will use off-the-shelf cell phone technology to construct a single-frequency GPS array of sensors to study the ionospheric effects of the eclipse. This project could help lay the foundation for eventually using smartphones to help monitor the outer atmosphere for disturbances or space weather events caused by solar storms. Meanwhile, the National Solar Observatory and the University of Arizona Citizen Continental America Telescopic Eclipse Experiment will rely on volunteers from universities, high schools and citizen scientists for a sort of eclipse relay race. Participants spaced along the path of totality will use identical telescopes and digital camera systems to capture high-quality images that will result in a data set capturing the entire 93-minute eclipse as it crosses the United States. Meanwhile, a project led by the University of California, Berkeley, will assemble a large number of solar images obtained by students and amateur observers along the path of the eclipse to create educational materials as part of the Eclipse Mega Movie project. You're listening to Space Time. I'm Stuart Gary. Scientists have discovered molecules that could form precursors for life on Saturn's moon, Titan. The researchers detected significant quantities of vinyl cyanide, which can naturally coalesce into microscopic spheres resembling cell membranes. The findings, reported in the journal Science Advances, means that under the right conditions, like the pools of hydrocarbons found on Titan, molecules of vinyl cyanide can link together to form membrane features, resembling the lipid-based cell membranes of living organisms on Earth. The discovery is based on a study of data from the European Southern Observatory's Atacama Large Millimetre Submillimetre Array Telescope ALMA, located in Chile. Titan is one of the solar system's most intriguing and Earth-like bodies. It's nearly as large as Mars, and it's the only place other than Earth where rain falls to form rivers, which then flow into lakes and seas. However, at 10 times the distance from the Earth to the Sun, Titan is so cold that water forms much of the surface bedrock, so the liquids on Titan are hydrocarbons. Titan has a hazy atmosphere made up mostly of nitrogen, with a smattering of complex organic carbon-based molecules, including methane and ethane hydrocarbons. Planetary scientists theorize that this chemical makeup is similar to Earth's primordial atmosphere. The conditions on Titan, however, are not conducive to the formation of life as we know it because it's so cold. The study's lead author, Maureen Palmer, from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says the presence of vinyl cyanide in an environment with liquid methane suggests the intriguing possibility of chemical processes that are analogous to those important for life on Earth. Previous studies by NASA's Cassini spacecraft, as well as laboratory simulations of Titan's atmosphere, inferred the likely presence of vinyl cyanide on Titan. But it took ALMA to make the definitive detection. By studying the ALMA data, Palmer and colleagues found 3 distinct signals, spikes in the millimetre wavelength spectrum, which correspond to vinyl cyanide. These telltale signatures originated at least 200 kilometres above the surface of Titan. And Titan's atmosphere is a veritable chemical factory, harnessing light from the Sun and the energy from fast-moving particles orbiting around Saturn to convert simple organic molecules into larger, more complex chemicals. To find out more, Andrew Dunkley is speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
Saturn's moon Titan may have revealed a pretty incredible secret.
Well, indeed, it already has, actually, Andrew. The molecule in question has been detected in Titan's upper atmosphere. So what molecule are we talking about? Well, we're talking about something called vinyl cyanide. And, of course, you and I, as soon as any word comes out that's got cyanide attached to it, we reel with horror.
Alarm bells.
Alarm bells start ringing. But the vinyl cyanide detection actually has come from ALMA, the Atacama Large Millimetre Array, an array of telescopes at about 5,000 metres high up in the high Atacama, not very far from San Pedro de Atacama. This is a radio telescope, essentially, that particularly looks at molecules, these atoms joined together to form the chemical compounds that we're all familiar with. And the news from ALMA is that they have detected vinyl cyanide in the upper atmosphere of Saturn's moon Titan. Now, Titan, of course, one of the most interesting places in the solar system, certainly the only other place known in the solar system, in fact, the only other place known in the universe so far, apart from the Earth, that has bodies of liquid on its surface. It's got seas of methane and ethane on its surface, an atmosphere that is largely nitrogen but has a fair bit of methane and ethane in it, making this kind of hydrocarbon smog that blankets Titan in this fairly horrible brown, foggy atmosphere. However, many people think Titan is a model for the early Earth, that it's a bit like the Earth was in its early history, in its prebiotic history, if I can put it that way, before life existed. With the one big difference, on Earth, of course, being nearer to the sun and in the sun's habitable zone where the temperature's just right for liquid water to exist, life on Earth formed with water as the working fluid. But on Titan, the working fluid for any life might well be this liquid natural gas, methane and ethane. And what is exciting scientists about the discovery of vinyl cyanide is it's a molecule that we use actually on Earth in the manufacture of things like synthetic rubbers, plastics, all these polymers that that we use in everyday life. And that gives you a hint as to what its role in nature might be, because it could be a mechanism for forming cell membranes. In other words, a membrane that will actually hold in the genetic components of, say, a microbe based on hydrocarbons rather than based on water. It's thought that it will be easier for life to kick off if you've got some method of holding the working fluid, in a fairly confined volume, rather than just having these molecules wandering around in the open sea, for example, here on Earth, or the open Titanian Sea up on Titan there, because there are seas on Titan. The liquid is not water, it is, as I said, liquid natural gas. So maybe, just maybe, this might provide a way that microbial life of a very different kind from what we find on Earth could kick off on Titan. And that's why everybody's excited.
But they're not suggesting that there is life on Titan. They're just suggesting there are signs that life could develop at some stage. Or are they saying there might have been in the past?
It may even be there already.
Okay.
So the detection is of these molecules high in the atmosphere of Titan, but actually that's where ALMA looks. But there seems to be a deal of confidence that such molecules will find their way down to the surface, because there's rain that falls on Titan. It's not water rain, it's methane rain. And there's a kind of haze of particles that drifts down from the upper atmosphere of Titan. Maybe these molecules have been carried down with that, and maybe there are enough of them, around near the surface for cell walls to have formed and for early biology to be taking place. There is another little snippet to this story. It goes back to the very early days of the Cassini space probe. Of course, Cassini's still in orbit around Titan until the 15th of September. These measurements weren't made with Cassini, they were made with ALMA, as I said. But Cassini made some measurements of a depletion of hydrogen and acetylene near the surface of some of these lakes and seas on Titan. This is back 12 years ago, 11 years ago. That was something that excited astrobiologists, because there had been a prediction made that if you had microorganisms which used ethane and methane as their working fluid, they might consume acetylene and breathe hydrogen. Both these things are actually depleted near the surface of the lakes. I don't know whether that observation has ever been confirmed, but it's one of these things that just hints gently towards perhaps Titan having living organisms. Maybe not now, but in the future.
Wow, that would be incredible, and something you and I have sort of hinted at time and time again, that it's only a matter of time before we finally make this discovery. What interests me, Fred, just as a sideline question, is how is it that a radio telescope can detect these things? It sounds like we're talking about a physical object, and a radio telescope sounds like something that doesn't actually pick up physical objects. So how does that work?
So what radio telescopes do is they look for molecules in a state of excitement. So a visible light telescope, we're looking at a cloud of gas, excited gas in space. We look at the way the atoms of that cloud of gas behave, and we can tell what the gas is made of by the response of the atoms. Same thing happens with molecules, but in radio telescopes. So, ALMA is particularly good at probing these gaseous envelopes, whether they're disks of gas around protostars, stars that are just forming, or around places like Titan, and particularly good at sorting out what molecules are there.
So if there is life on Titan in some form or another, how long before we could either confirm or deny the existence of life?
Yeah. I know, that's the trick. You know, there are missions being planned to Titan, but they're only in the very, very early stages. And these things have a 20-year lead time. And then it's kind of, well, it was 7 years for Cassini to get to Saturn from the Earth. That's the kind of typical journey time.
Yeah.
It's not a quick process.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. The SpaceX Falcon 9 rocket has blasted into orbit, carrying the Dragon CRS-12 capsule to the International Space Station. The Falcon 9 launched under brilliant blue skies from Pad 39A at the Kennedy Space Center at the Cape Canaveral Air Force Base in Florida.
Falcon 9 is configured for flight.
9, 8, 7, 6, 5, 4, 3, 2, 1. The liftoff of the Falcon 9 takes flight with the Dragon spacecraft destined for the one-of-a-kind laboratory in microgravity, the International Space Station.
And the Falcon 9 has cleared the tower.
39A, form the launch pad, post-launch operations. Copy, we'll go.
By for the Falcon 9 to go transonic at a minute 6 seconds after liftoff.
2 seconds later,
thereafter by
2 seconds later, we'll go through max Q, which is the maximum dynamic pressure on the vehicle.
Power to launch nominal.
standing by for Falcon 9 to go transonic.
Passing through max Q.
Next major milestone will be the shutdown of the 9 Merlin engines. Scheduled for 2 minutes 27 seconds into flight. Less than a minute away from main engine cutoff.
MVAC engine chill has begun.
After main engine cutoff, the first stage will perform a boost back burn about 15 seconds later and head back to nearby Cape Canaveral Air Force Station Landing Zone 1.
Station 1 jettison will begin at 2 minutes 29 seconds.
Vehicle flying down the nominal. We have MECO.
And we have MECO.
Stage separation confirmed.
The stage separation, stage 1 drifting back away from stage 2, continuing to power Dragon into space.
Second stage ignition.
Engine has ignited, and that's the first stage, heading back toward the ground, just miles away from the launch pad. First stage is conducting a boost burn, about 10 seconds remaining in that burn.
Dragon nose cone deploy.
Meanwhile, the Dragon nose cone has deployed, exposing the
Trajectory
Dragon
nominal.
spacecraft to space.
Boost back shutdown.
Boost back burn shutdown. Everything proceeding normally with both first and second stage operations of the Falcon 9. First stage continues to fly
Acquisition
upward,
of signal Bermuda.
reaching its apogee in about 10 seconds before it makes its descent toward Earth. About 4.5 minutes after launch, everything continues normally. The second stage engine will continue burning for about another 5 minutes. Falcon 9 first stage, counting down toward its entry burn in about a minute and a half. Thrusters firing to control the first stage as it makes its way back toward Earth. Once again to land at Cape Canaveral Air Force Station Landing Zone 1, accompanied by a sonic boom for those who are in the area. 5.5 minutes after launch, everything continues to go normally for the Falcon 9 first stage and for the second stage and Dragon spacecraft.
Have acquisition at New Hampshire.
New Hampshire tracking station, now tracking the vehicle, less than 30 seconds away from the first stage entry burn. Landing of the first stage, scheduled in about 1 minute, 45 seconds. And we have the entry burn underway.
burn.
And the entry burn has
Entry
ended.
shutdown. Stage 2 still on nominal trajectory.
Stage 2 still on course for its rendezvous with the International Space Station. Stage 2 engine
Stage one
cutoff about
AFTS
2.5
station.
minutes away from now. Stage 1 about to come back subsonic, about 45 seconds away from landing.
Transonic.
Stage 1 is transonic. Landing burn about to begin.
S1 landing burn.
Landing legs will be deployed in about 15 seconds. And a sonic boom felt throughout the Kennedy Space Center and Cape Canaveral Air Force Station area as Falcon 9 first stage
Landing legs deploy.
Returns to Cape Canaveral Air Force Station, landing zone 1.
LZ-1, the Falcon has landed. Landing operators move into procedure 11.100, section 3 on LZ-1 net.
Meanwhile, Dragon spacecraft, powered by the Falcon 9 second stage, continues on its way to orbit with a second stage engine cutoff expected in about 1 minute. Everything is proceeding per the timeline. 40 seconds away from second stage engine cutoff.
Stage 2 is under terminal guidance.
Stage 2 AFTS is saved.
9 minutes after launch, everything continues to go well. Second stage burn is about to end, and spacecraft separation about 1 minute away.
Yes, SECO.
SECO, second stage engine cutoff confirmed.
GNC confirms good orbit insertion.
Guidance, Navigation, and Control Officer confirms good orbit insertion.
Dragon separation confirmed. Dragon is on its way to the International Space Station.
And Dragon is on its way to the International Space Station, the Mission Control Center in Hawthorne, California, where SpaceX is headquartered. Great mission so far. The Dragon is on its way to the space station, controlled by the International Space Station Control Center in Houston, Texas, standing by for solar array deploy of the Dragon spacecraft.
Dragon separation confirmed.
And there's Dragon separation. That will be followed by the solar array deploy in about a minute. 10.5 minutes after launch. Stage 1 back on the ground. Stage 2 just deploying the Dragon spacecraft.
Dragon was captured by the orbiting outpost robotic arm and moved to a docking port on the Harmony module. The mission transported some 2,910 kilograms of supplies and equipment to the orbiting outpost. The primary payload aboard Dragon was CREAM, the Cosmic Ray Energetics and Mass Investigation Project, which will study cosmic ray particles entering Earth's atmosphere over at least the next 3 years. The refrigerator-sized NASA experiment will be attached to the outside of Japan's science module, from where it will study cosmic rays bombarding the Earth. Cosmic rays are high-energy ionized particles which originate both from the Sun and more mysteriously from deep space. Cosmic rays reaching the Earth from beyond the solar system have enormous energies, well beyond that of man-made particle accelerators. Space-based direct measurements of high-energy cosmic rays are difficult because of low particle fluxes in the most interesting regions. And there's no data sets with elemental charge resolutions with adequate statistics. And that's where CREAM comes in. It'll study different types of cosmic rays from protons through to ion nuclei, measuring their mass and energy ranges. 6 previous CREAM missions were all flown on high-altitude balloons, up to 40 kilometres or 130,000 feet above the ground. The balloon-based CREAM observations accumulated some 161 days' worth of data. By placing CREAM aboard the International Space Station for long-duration exposure above the atmosphere, scientists will get orders of magnitude greater statistics and without the secondary particle background inherent in balloon experiments. The data collected by CREAM will address fundamental questions about the origins and histories of cosmic rays, building a stronger understanding of the basic structure of the universe. Dragon is slated to remain docked to the orbiting outpost until at least mid-September. It'll then return over 1.5 tons of completed science experiments and hardware back to Earth, splashing down in the North Pacific Ocean off the California coast. The Dragon being used for the CRS-12 mission is expected to be the last scheduled use of a newly built Dragon capsule for some time. SpaceX plan to use previously flown Dragons on future missions to the International Space Station. This flight was also SpaceX's 11th Dragon resupply mission to the orbiting outpost. The Hawthorne, California-based company has a contract with NASA to fly 12 resupply missions through to 2019 with an option for a further 6. CRS-12 was also the 11th SpaceX launch for 2017. 9 more are slated before the end of this year. The next SpaceX Falcon 9 launch will see Taiwan's Formosasat 5 Earth observation satellite take off from the Vandenberg Air Force Base in California, slated for August 24. And next month, on September 7th, SpaceX will carry out its first launch of an X-37B US Air Force space shuttle. This will be the 5th flight for the winged reusable spaceplanes, which are being used for classified long-duration missions. The flight, known as OV-5, will launch from the Kennedy Space Center. All previous X-37B flights have used United Launch Alliance Atlas V rockets to get into orbit. I'm Stuart Gary. This is SpaceTime. And now time to take a brief look at some of the other stories making news in science this week with a science report. And a new study has uncovered a link between being overweight or obese in adolescence and an increased risk in developing colon cancer in later life. The report by the American Cancer Society also found obesity to be associated with an elevated risk of developing rectal cancer. The findings come at a time of growing concern about the impact of adolescent overweight and obesity on chronic disease in later life. Previous study results on a potential link between adolescent obesity and the risk of colorectal cancer in later life have been conflicting, and too many study designs have been limited. So to provide more clarity, scientists at Tel Aviv University in Israel analysed information from over 1 million males and 700,000 females, including their body mass index, between the ages of 16 and 19, between 1967 and 2002. The subjects were then followed up until 2012. Over an average 23-year follow-up period, 2,967 new cases of colorectal cancer were identified, including 1,977 among men and 990 among women. Being overweight or obese was associated with a 53% higher risk of colon cancer in men and 54% in women. Obesity was also associated with a 71% increase in rectal cancer in men and more than a twofold increased risk in women. The South Australian town of Port Augusta is to get the world's largest solar thermal power station. Work on the 150 megawatt plant 30 kilometres north of town will start next year. The $650 million facility will power some 90,000 homes, with supply expected to be online by 2020. Solar thermal uses mirrors known as heliostats, which follow the sun's path across the sky, to concentrate sunlight onto a tower that heats molten salt, which is then used to produce steam to spin turbines and generate power. Similar scale solar thermal power stations are already operating in both Nevada and Spain. Australia's first solar thermal power station was constructed in 1981 at the town of Whitecliffs in outback New South Wales. The experimental facility developed by the ANU used 14 3-metre parabolic dishes, each covered by over 2,000 mirrors, and mounted on a heliostatic base. The dishes followed the sun across the sky, focusing the sun's rays onto a collector where water was boiled to drive an engine and generate power. The facility was mothballed in 2004. The Port Augusta solar thermal power plant follows last month's announcement by Elon Musk to build the world's largest Tesla battery power station on a wind farm near Jamestown, also in South Australia. The 100 megawatt, 129 megawatt hour facility will be able to store enough energy to power 4,000 homes for up to 24 hours. A new study has confirmed that the age at which boys are first exposed to pornography will significantly influence certain sexist attitudes in later life. The findings, presented to the 125th Annual Convention of the American Psychological Association, surveyed 330 males aged 17 to 24. They were asked their age when first exposed to porn, in order to see how that influences promiscuity and male domination over women. The researchers from the University of Nebraska in Lincoln found the average age at which boys were first exposed to porn was usually around 13.37 years. The youngest were exposed at the age of just 5. The oldest was over 26. Accidental first exposure to porn accounted for about 43.5% of cases, while 33.4% were intentional and 6% didn't indicate the nature of their first exposure. Disturbingly, some 17.2% of first exposures to porn were forced. Researchers found that the younger a boy was when he was first exposed to pornography, the more likely he was to want power over women, while the older a male was when first viewing porn, the more promiscuous he was likely to be. This finding was somewhat of a surprise to researchers, who expected both domination over women and promiscuity to be higher with early porn exposure. The findings could be related to variables, such as religious attitudes, sexual performance anxiety, negative sexual experiences, or whether that first exposure to porn was positive or negative. A new study has revealed that West Antarctica's vast ice sheet conceals what may be the largest volcanic region on Earth. The findings, reported in the Geological Society's special publication series, claims the continent's ice covers more than 100 newly discovered volcanoes. Geologists and ice experts say the range has many similarities to East Africa's volcanic ridge, which is currently acknowledged as being the densest concentration of volcanoes on Earth. Researchers from the University of Edinburgh remotely surveyed the underside of ice sheets for hidden peaks of basalt rock like those of other volcanoes in the region whose tips pushed above the ice. They analysed the shape of the land beneath the ice using measurements from ice-penetrating radar and compared the findings with satellite and database records as well as geological information from aerial surveys. Scientists found 91 previously unknown volcanoes ranging in height from 100 to 3,850 metres. The peaks are concentrated in a region known as the West Antarctic Rift System, spanning some 3,500 kilometres from Antarctica's Ross Ice Shelf to the Antarctic Peninsula. The findings didn't indicate whether the volcanoes were active, but it should inform ongoing research into seismic monitoring of the area. One of the big fears right now is that volcanic activity may increase if Antarctica's ice continues to thin. And that's likely as global warming caused by anthropologic greenhouse gas emissions continues to spiral out of control. And finally for now, a report in the Journal of Experimental Psychology claims people with higher cognitive abilities are more likely to learn and apply social stereotypes. The results, stemming from a series of experiments, also show that those with higher cognitive abilities are also more likely to discard stereotypes when presented with new information. While superior cognitive abilities are often associated with positive outcomes, such as academic achievement and social mobility, the new findings show that some cognitive abilities clearly have negative consequences. Stereotypes are generalizations often inaccurate about the traits of social groups, which are then applied to individual members of those groups. Because pattern detection is a core component of human intelligence, people with superior cognitive abilities may be better equipped to efficiently learn and use stereotypes about social groups. The researchers reached their conclusions after conducting a series of 6 experiments on a total of 1,257 subjects. The findings confirm that people with better pattern detection abilities are at greater risk of picking up on and applying stereotypes about social groups. However, what was promising about the findings is that people with higher cognitive ability also tend to more readily update those stereotypes when confronted with new information. You're listening to Space Time. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.